Okay, so we'll continue on with our development of integrals in the complex realm. And we'll look at section 4.39 on contours. Contours are the things we'll integrate over. So this is sort of the last in the preliminary stuff before we get down to really integrating. We'll have definitions in the next section and examples in the section following that. So we'll define contours. These are the kinds of curves over which we'll integrate. In Calculus 1, you integrate over intervals, closed and bounded intervals in Calculus 1. Later, you integrate over discontinuities and deal with improper integrals. So this is our foundation. These contours play the roles of closed and bounded intervals. Integral from A to B from the real setting will be integral over a contour C in the complex setting. So we'll take a set of points, z equals xy or x plus iy, depending on your notational tastes. Set of points in the complex plane is called an arc. If x is a function of t and y is a function of t, where t ranges from A to B. We want a little more structure to it than just this arc stuff in our definitions of contours. But this gets us started with paths, in a sense, in the complex plane. We are requiring x of t and y of t to be continuous functions of the real parameter. And we'll denote the arc C as z of t equals x of t plus iy of t, where t is ranging from A to B. A little bit of hypotheses. We'll be taking integrals from A to B initially here as well. An arc arc C is a simple arc, or Jordan arc. It's pronounced Jordan. If it does not cross itself, that is, z of t1 and z of t2 are distinct, provided t1 and t2 are distinct. You think of t as time. That's why they've chosen t for the parameter. And we'll start at time A and start at complex numbers, z of A. And then as time goes by, we'll trace out some trajectory in the complex plane, ending up at z of B, when t equals a final value in the interval over which we have the parameterization. We said A to B above. So the curve doesn't double around and pass through the point twice. One special type of arc is simple, except at its endpoints, maybe z of B and z of A are the same. So the only place we have intersection is at the endpoints. Such an arc is called a simple closed curve, or sometimes a Jordan curve. So it's kind of a circle that's been bent and twisted potentially a little bit, depending on how wild the contour, the arc C is, depending on how involved the z of t and the z of the x of t and the y of t functions are. They're real and imaginary parts that have parameterized the arc. For us, no problem. They'll be nice, continuous, even differentiable curves with a couple of other little constraints. So what a simple closed curve is think of it as a circle that's been maybe bent and twisted a little bit. Hasn't been, take a loop of string and throw it on the table. It doesn't overlap itself. There's none of that. And that's simple means there's none of that. But being some type of bent circle, if you like, we can talk about an orientation in terms of clockwise or counterclockwise for a simple closed curve. These are said to be positively oriented when it's traced out in a counterclockwise direction, as t ranges from the beginning to the end as time goes by, as it were. It traces around the curve in a counterclockwise direction. And you know from your trig experience in the old days, counterclockwise is the direction of positive angles when we talk about angles in, say, the Cartesian plane in the trig setting. So same idea here. The unit circle, z equals e to the I theta. As theta ranges from 0 to 2 pi, that's a simple closed positively oriented curve. It is a circle. Here's another circle, z equals e sub 0 plus r e to the I theta. That's a circle with centers e sub 0 and radius capital R. Theta ranging from 0 to 2 pi. Now, we're often going to deal with integrating around circles. So we talked above about parameterizations with respect to t. Well, when we deal with circles, it'll be common to parameterize with respect to theta. So the t's become thetas, the dt's become d thetas, and so forth. Arcs do not have unique representations. The arc was actually, you dissect the definition, it was the collection of points in the complex plane and not how those points were generated. And ultimately, we're just interested in the collection of points itself, not how that was parameterized. If we have some particular parameterization, z of t, for an arc, we could take t, say, replace it with t cubed, adjust the endpoints accordingly, maybe replace the t equals a with an initial value of cube root of a. So when we substitute that into the t cubed, we get a back out. There's different ways to parameterize the curves. We want to set up integrals that are dependent only on the arc itself, only on the collection of points, not on how that arc is parameterized. This will lead us to deal with some U substitution type stuff, it turns out. If we had, say, t equals phi of tau, where tau ranges from alpha to beta, and phi maps the interval, alpha to beta, onto the interval a to b, we could re-express these arcs in terms of taus and instead of in terms of t's. So the story on that is we've got a situation like this. We're going to assume phi is continuous and it has continuous derivative. And this will have some physical meaning, phi prime of tau is greater than 0. So what we've got here is a t-axis. T ranges from a to b. We've got a tau axis. Tau ranges from alpha to beta. And phi of alpha equals a. So get this point here. Phi of beta equals b. And what we're doing is dealing with a function of a parameter versus the contour itself. This is not the complex plane. This is the tau t Cartesian plane. But we're told continuity, you know what that means graphically. We're told phi prime of tau is greater than 0. So the phi function itself, phi of tau, must be an increasing function, as drawn here. So we couldn't have that function go up and oscillate around. That's not allowed in what we're doing here. Yeah, that'd generate, as tau goes over its values, repetitions in the t values, and what it'd amount to in terms of a contour is moving forward and back along a contour. We don't want that. We want always moving forward along the arcs in terms of how they're parameterized. We don't want repetitions of input values. So in such a case, we could take arc C, parameterize with respect to t, and re-express it, same collection of points in the complex plane, express it as z of tau, capital Z of tau, where we've done a composition of the lowercase z that we had over here and this phi function. So that allows us to change representations of arcs from in terms of one parameter t to in terms of another parameter tau, where I know some relationship between the t's and the taus, for example, given by a function phi. All right, suppose we got an arc expressed as z of t equals x of t plus iy of t, t ranging from a to b. If x prime of t and y prime of t are continuous, then this is called a differentiable arc. So differentiable arcs are, it's a little misleading, they're a little more than differentiable. Not only do the derivatives x prime and y prime exist, but they're continuous. It's called continuously differentiable. Cool, this conversation of x of t and y of t and x prime of t and y prime of t, that's all real stuff. So it's really all just calculus 1 stuff. We're interested in differentiable arcs because we can define the length of a differentiable arc. It is defined as length of differentiable arc C with this parameterization is the integral from a to b modulus of z prime of t dt. Well, you know what z prime of t is because you've got the components here, x of t plus iy of t. Real part of z prime would be x prime of t. Imaginary part of z prime would be y prime of t. So we'll square those, add them together, take the square root. That's how you find moduli. And this might look familiar to you from Calculus 2, where you do arc lengths. The reason we've imposed this condition of differentiability, that is of x prime of t and y prime of t being continuous, if x prime and y prime are continuous, then this integrand is continuous. What kind of functions do you know how to integrate? Fundamental theorem of calculus says, well, I can use antiderivatives if I have continuous functions. Another result from calculus 1 says, you got a continuous integrand, the Riemann integral exists. Okay, so we won't have any problems with non-existence from the real stuff in terms of calculating lengths like this. If you'll go back and look through your calculus 2 notes, when you defined arc length, you took the arc length of smooth functions, and the word smooth meant exactly this. X prime of t and y prime of t were both continuous if you had a curve back then defined parametrically. But smooth means a little more than differentiable. It means continuously differentiable. And the reason for that was, hey, as long as the integrand is continuous, the integral exists. So that was the motivation in calculus 2, and it's the same stuff here. The integrand's continuous, then the integral really exists. That's guaranteed. Integrals of continuous functions exist. Integrals of some discontinuous functions exist as well. See senior level analysis for more details on that, though you do integrate over discontinuities even in calculus 2. It really reaches its complete explanation in probably a graduate real analysis class where you classify what kind of functions are Riemann integrable. The punchline is a function's Riemann integrable if it ain't too badly discontinuous. What that means is a pretty long story. Here, we got C parameterized, say, in terms of tau. Say t equals phi of tau, kind of in the picture we had above. We could deal with a change of variables and express that length not in terms of t, but in terms of tau, which is apparently to be shown in some of the exercises. Does this make sense? Well, pretty much. What we do is simply take the t and substitute in t equals phi of tau, do that change of variables in there. The dt, just like when you do u substitution, we'd calculate dt, the differential, is phi prime of t d tau. So the dt becomes exactly this part here. It's really just a u substitution, and that's how that'll be justified. Oh, but u substitution only works in the real setting, so you'd have to go through the details, if applicable, to isolate real and imaginary parts. There really is no complex stuff in this computation of arc lengths. Turns out this is all real stuff, so it's just straight up u substitution. Little comment about this length. Its definition, you can't argue with it, but you know that definition, it ought to make sense. Think physically. Think of t as time, and what we've got here, modulus of z prime. Well, if these were vectors, and we'll mention vectors, and we've associated vectors with complex numbers, we'd think of think of Z prime maybe as a velocity vector. You would in calculus 3. So we think of the modulus of that velocity as speed. So if you thought in terms of units and little slices the way you would in calculus 2, what we got here is a little slice of speed times a little slice of time. Speed might be meters per second. Time would be seconds. Multiply those together, you get meters, and then you add them up. Now that's horribly informal because integrals are not sums, they're limits of sums, but it gives some intuition about the fact that, oh yeah, it makes sense that this is a definition of the length of a curve expressed in the complex setting, because it looks just like the way you did it in R2 back in calculus 2 or 3. Speaking of vectors, a passing comment about associating vectors with complex numbers. If we've got a differentiable arc C and the derivative is not 0, Z prime of t is not 0, we're going to do some division by that. Then we have the unit tangent vector, Z prime of t divided by modulus of Z prime of t. So we've taken this Z prime of t and divided it by its magnitude. We've normalized it. The resulting thing is length 1. If we interpret it as a vector, then it's a unit vector. So if we have a path, this t vector just points in the direction of travel as time goes by. Think physically as well. You're flying around on this arc in the complex plane, and this vector is telling you which direction you're going. A little more tangibly would be driving around in R2 and expressing a curve parametrically. The t vector points in the direction of travel. You turn the steering wheel and the t vector changes direction. So it's a similar idea here. We're muddling the difference between complex numbers and vectors in R2, which we've done in the past, but it gives a little physical interpretation to this t vector. And if you do anything with curvature of paths, it's very much related to the change of this unit tangent vector, the direction of travel vector. For more details, check it out in Calculus 3. This talk of vectors is really a more appropriate conversation for R2 or R3 and for calculus, where things are real. All right, we finally get to defining a contour. Differentiable arc C, given by Z of t ranges from A to B, is smooth if Z prime of t is continuous, so if the derivative is continuous, for all t between A and B, and Z prime of t is not 0 to the interior of that interval. So you think you start, you move around, and you don't stop until you get to the t equals B value. So Z prime of t is not 0 means we started, we moved, we didn't stop, we certainly didn't back up. If the derivative is non-zero, it can't, in a sense, change from positive to negative. That doesn't have sense because we're in a complex setting here. Its magnitude can't change from positive to negative. You couldn't have traveled forward and stopped and gone backwards. That point at which you would stop, being nice and smooth as required above, would mean that the derivative had to go to 0. So there's no repetition of going back and forth over the same points. That we don't want. That's going to mess up our integrals. So a smooth arc is given. A contour, also called a piecewise smooth arc, but we'll stick mostly with the lingo of contour, is an arc consisting of a finite number of smooth arcs joined end to end. So nobody said I can't have maybe sharp points in a contour, but we're going to have a nice smooth arc joining another nice smooth arc, joining another nice smooth arc. Where they join up, all bets are off. We are requiring continuity, but it could be we have sharp points, and we'll see some examples in the next section, I think it is, of contours that are only piecewise smooth. And you've probably dealt with this in applied math, or maybe even in some of the calculus stuff when we talk about piecewise smooth. When the initial and final values of z of t, where z of t is a parameterization of a contour, are the same. That contour is called a simple closed contour. So here we've got something that is, it's similar to a bent circle. Homotopic is the word the topologists use. And when you have a simple closed contour, then there's a famous theorem from topology that says a simple closed contour in simple closed curve, simple closed contour in the plane divides the plane into two regions. One bounded, the inside of the contour, and the other one unbounded, the outside of the contour. It's called the Jordan curve theorem. Again, pronounced Jordan, same dude. The book we usually use around here in topology, Munckery's Topology, has a chapter on these separation theorems. And funny thing, that same chapter includes some stuff on the Cauchy integral formula. Hey, we're going to do the Cauchy integral formula. We'll do it in section 50 in here. So this integrals of complex variable, you're going to probably see this again. You'll see it again in applied topics, quite likely. It has applications. We won't have time to do them, but it has applications actually to certain real integrals. Definite integrals of a real valued function of a real variable. There's ways to approach those in terms of some things involving complex integrals. So it has lots of applications in straight up applied math and evaluating integrals, which could have applied math applications, and even in this more esoteric stuff of topology. We have a cross-listed senior/graduate level class in topology where, time permitting, you would cover this kind of thing. Let's move on to setting up integrals with respect to contours.